Okay. Before we start doing RSA encryption, we have to learn what mod means. Or, in coding, it's going to be the percent symbol. So, what mod is let's think of a clock right here. We know that it goes 12, we have 6, 3, and 9. And all the numbers in between. So, what happens here is we know that, let's say, normally we'll have 12 plus 1 is 13. But for a clock, unless you're using the 24-hour clock, we're going to have 12 plus 1 isn't going to give us 13, it's going to give us 1. So we're going to put 3 lines is equal to 1, and it's mod 12, because we're only using 12 numbers. So let's say, in this imaginary world, we have a 13-hour clock for some reason. And we say we have 7 plus 9. So normally, that's going to be 16. But in our imaginary world, where we want to use mod 13, because of our 13-hour clock, we're going to have 7 plus 9 is equal to, now we know that it's normally 16, but we have to take that, what we're going to do is we're going to take 16 divided by 13. Or 13 goes into 16 only one time. So now, if you remember long division, we're going to have a remainder at the end. And that remainder is going to be whatever number we get. So since this one's nice and easy, we know 13 goes into 16 one time. So if we write this up here, 16 divided by 13, 0, 1, minus 13, it gives us 3. So we know that our remainder is 3, which is our new answer for 7 plus 9 mod 13. So next, what we're going to do is we're going to do just another example. I'm going to write a couple out, and I'll give you a minute to try them before we take them up. So I'll give you a second to test those out, and then we'll take them up. Okay, so I hope you had a second to try them out, and we're going to take them up now. So we're going to start off with 11 plus 11 mod 3. So we know 11 plus 11 is 22. And to start off, we're going to take it in long division by 3. So 3 and 2, that's 0. Gives us 2, and then we bring down this number 2. So 3 goes into 22 now 7 times, because we're going to subtract 21. And that gives us 1 as our remainder. Now this remainder is going to be what's left over, which means this is what is going to be here. So our answer, instead of being the question mark, is going to be 1. So 11 plus 11 mod 3 is congruent to 1. Next is going to be 27 plus 2 mod 7. So we know that this is 28 or 29, and we're going to divide it by 7. So 7 goes into 0 times. So we take that, then we bring down the 9. That 7 goes into 29 4 times. So we subtract 28, and this gives us 1 as a remainder again. So this remainder is now what our answer is going to be for 29 mod 7. Some good examples I grabbed. And now, our last one is 4 plus 4 mod 2. Well, 4 plus 4 is 8, and we're going to divide it by 2. But this is just 4, so it's going to be 0. So 4 plus 4 mod 2 is just going to be 0. Okay, today we're going to be doing RSA encryption. So what RSA encryption is it is just like a mailbox. What's going to happen with this mailbox, which is beautifully drawn, is it's going to have, let's say it's indestructible. The location of this mailbox is going to be public knowledge. So we're going to say this is known as a public key, because anyone could go to this mailbox and check it out. But let's say that there's a little keyhole right here, which only one person has the key to. That's what we're going to call the private key, just because only one person has it and no one else can get into it. So for this, we're going to make a character. His name is Bob. Bob wants to send a message to Alice. However, this message, if it's not protected properly, could be intercepted by a lady named Eve. So for RSA encryption, what Alice needs to do is she needs to choose two very large prime numbers, which is going to be known as P and Q. So since those are two very large primes, what she's going to do now is she's going to find this letter N, which is P multiplied by Q. Then step 3, what she's going to do is she's going to compute the phi of N, which is going to be equal to the phi of P and Q. So if you remember anything about phi, what it is since these are both prime numbers, it makes it a lot easier for us, because now all we got to do is find the phi of P and multiply it by the phi of Q. But since they're prime numbers, we can just use the simple rule where it's P minus 1 multiplied by Q minus 1. Okay. So then step 4 is Alice is going to choose an integer, any integer, as long as it's greater than or equal to 3, which is going to be given the letter E for encryption. It's very creative. So then what we're going to do is we got to check that E has the greatest common denominator of E and phi of N, which remember before is just the phi of P and Q. All of this is equal to 1. Then step 5 is Alice will compute a number or a letter known as D, such that E multiplied by D is equal to 1 mod phi of N. And finally is part 6, where Alice puts all these calculations out there for everybody. So the public key, which if you remember is the location of the mailbox, is going to be N and E. So whatever her N is and whatever her E is, she could give to anybody, and that's no problem. But she's going to keep the secret private key just for herself, which is known as N and D. So to simple it down and kind of recap, we're going to have, and I'll show you why this works. So we have M, which is going to be the plain text. It's just going to be whatever message that Alice wants to send. And then with this calculation, we're going to have whatever our text is raised to E that we're going to use for encryption. We're going to have it all mod N, which will give us C, which if you remember is just the cipher text. It's our encrypted data. And then this is what our C is what Bob sends to Alice. Now, the way that it works for Alice to decrypt this code is Alice is going to take C and put it to the power of D, which is a part of her secret code that no one else has, and she's going to put it mod N. So this is going to become E, or M, to the E, to the D. All of this is going to be mod N. However, if you remember exponent laws, it's going to be M to to the E multiplied by D mod N. And then, but E multiplied by D is 1 plus K phi of N. If you believe me, you'll just know that this is correct and you won't question it. So then this is going to be M to the 1 plus K phi of N from before, mod N. But this is all going to just become M multiplied by M to the power of phi of N to the K. Because this is going to be M to the 1 and this is going to be M to the rest. And then this is going to be all equal to 1. So all we're left with is M mod N, which is the exact message that Bob sent to Alice. Okay, now we're going to create an easy code just for a little bit of encryption, and then we're going to do a short decryption code after. So to start, we're going to import numpy as np, which just allows us to do calculations and everything that we need to do for this. So just as before, we need to have a plain text message. To make this easier for us, we're going to just put it as the number 8. Later on, we'll use letters and then change it to numbers, but to keep it easy, we're just going to use M is equal to 8. So then, what we're going to need to do is have our imaginary N, which it doesn't really matter what it is. So we're going to pick just a large number of 31.27. There's not really a meaning for it, it's just anything that's large for right now. And now we're going to have E is equal to 41 because it has to be greater than 3. And I already tested all these numbers, so it works with all the rules. So if you want to just test those out and try to find new ones, you can. So now we're going to create our first definition, which is going to be the power. So it's going to be B, X, and M. It doesn't really matter for this instance, so we can change it to our own letters and what we want to do for this. So we're going to have M, E, and N, just so that it's a little bit less confusing using different letters. So what this definition is going to be saying is if E is equal to 0, then we're going to return 1. However, else return B multiplied by the power of M, E minus 1, and N. All of this mod N. Now what we're going to say is we're going to say C, which is our encrypted text, is going to be equal to the power of M, E, and N, which is saying M to the power of E mod N. And now, when we have it print, we'll say this is the encrypted code or number, we'll say, and then we're going to list C. And we print, when we print, we have our new encrypted number of 1072. So it takes our number 8, which is our inputted number, and does all the calculations of M to the power E mod N and gives us 1072. So now, let's say we change our 8 and we want it to be 92, because that's our new message. It'll run through it again and it'll give us a new encrypted number. Now we're going to write the decryption code for the encryption that we wrote. So we're going to start off the same way with importing numpy as np. And then what we're going to do is we're going to input our C that we had before. So we're going to go with M is equal to 8, and we're going to use our C value as 1072. Now, what you're going to need to do here is you'll need to do a little bit of calculations that you learned from before to actually solve for the D if you want to use different numbers, but for this it's just 1177. It makes it nice and easy, and I already checked in, it works out good. And finally, we need to put our N from before, since that's a part of the public key. Anyone would have it either way. So then what we're going to want to do is we're going to use the same definition as power from before, but this time we're going to set it so that we have A, which was going to be our new answer, is going to be equal to the power of C to the power of D mod N. And this will give us back our original M value, which, if you remember, is just our original message. So this is the answer, comma, then we put A, and when I press play, we'll get 8, just like our original message.